In determining at what point and how much force to exert on a man-made satellite to change its path, the engineers need to calculate such quantities as the slope, the tangent line, the normal to a curve, and the rates of change. Hi, my name is Jason Rosenberry, and that's what we will be visiting in today's lesson. Let's get started with the average rate of change. The average rate of change of a quantity over a period of time is the amount of change divided by the time it takes. For instance, let's say we're trying to find the average rate of change of the function f of x equals e to the x over each time interval. Part A, we want to cover the interval from -2 to 0. So to find the average rate of change over the time interval from -2 to 0, so equal to, let's substitute 0 in first, so we would have e to the 0 minus e to the -2 divided by the amount of time, which was 0 minus -2. This is nothing more than the slope formula. E to the 0 minus e to the -2 is 1 minus e to the -2 all over 0 minus -2, which is 2. Part B, now our interval is from 1 to 3, so this would be equal to e cubed minus e to the first power, or e, over 3 minus 1, so we get e cubed minus e all over 2. We start with this idea and work with it to find the tangent to a curve at a certain point. Here's a description of what we can do. To find a tangent to a curve, 1, we start with what we can calculate, namely the slope of a secant through P and a point Q nearby on the curve. 2, we find the limiting value of the secant slope, if it exists, as Q approaches P along the curve. 3, we define the slope of the curve at P to be this number and define the tangent to the curve at P to be the line through P with this slope. More formally, we can define the slope of a tangent line as follows. Definition: slope of a curve at a point. The slope of the curve y equals f of x at the point P, which has coordinates a, f of a, is the number m, which equals the limit as h approaches 0 of f of a plus h minus f of a all over h, provided that this limit exists. Let's try an example. Let's let f of x equal 1 over x. A, find the slope of the curve at x equals a. B, where does the slope equal -1/4? C, what happens to the tangent to the curve at the point a, 1 over a for different values of a? Let's start with part A. Let's find the slope of the curve at x equals a. So for part A, we're looking for this value m, which can be found by limit as h goes to 0 of f of a plus h minus f of a all over h. Substituting our function, we get limit as h goes to 0, f of a plus h would be 1 over a plus h minus f of a is 1 over a, all that over h. Now we'll do some algebraic simplification. This would be equal to limit h goes to 0. We're going to multiply top and bottom of this fraction by the common denominator, a times the quantity a plus h. In doing so, we could also rewrite this limit as 1 over h times a minus the quantity a plus h over a times a plus h. Now we're going to simplify it. We're going to distribute the negative sign through. We can see that we end up with a minus a. That goes away, and we're left with a 1 times negative h in the numerator. So we currently have this equal to limit h goes to 0. We have 1 over h times negative h over that a times a plus h. We can now put our two fractions together. This is equal to limit h goes to 0 of negative 1 over a times a plus h. Now what happens when we substitute 0 in for h? We get negative 1 over a times a plus 0, or negative 1 over a squared. So there's the answer to part A, negative 1 over a squared. Part B would like to know, where does the slope equal negative 1/4? So we're going to set our slope expression, which we just found to be negative 1 over a squared, equal to negative 1/4. And we can see that the only way this is a true statement is if a squared equals 4, therefore a equals plus or minus 2. So there are two values of a such that the slope of the tangent line is equal to negative 1/4. So to find out the actual points, we will find both f of a, which in this case is f of negative 2, and also f of positive 2. F of negative 2 is negative 1/2. F of positive 2 is positive 1/2. So we have 2 points, negative 2 comma negative 1/2. Also the point 2 comma 1/2. At those points we have slopes of tangent lines being negative 1/4. Part C is asking what happens to the tangent to the curve at the point a comma 1 over a for different values of a. Well, our slope expression, negative 1 over a squared, it's always negative. So as a goes to 0 from the right side, the slope approaches negative infinity, and the tangent becomes increasingly steep. The same is true as a goes to 0 from the left. As a moves away from the origin, the slope approaches 0 and the tangent line becomes increasingly horizontal. The normal line to a curve at a point is the line perpendicular to the tangent at that point. Let's find a normal line. For y equals x squared at x equals negative 2, find a, the slope of the curve, b, the equation of the tangent, and c, the equation of the normal. D, then draw the graph of the curve, tangent line, and normal line in the same viewing window. So let's start with part A. Let's find the slope of the tangent line at x equals negative 2. So that slope m would equal the limit as h approaches 0 of f of negative 2 plus h minus f of negative 2 all over h. Simplify, we get limit as h approaches 0 of f of negative 2 plus h would be negative 2 plus h squared minus f of negative 2, or negative 2 squared, all over h. Now we'll expand the numerator, so that would be limit as h approaches 0 of 4 minus 4h plus h squared minus 4 all over h. One more simplification. We have limit as h approaches 0. In the numerator we have a 4 minus 4, which make 0, leaving us with negative 4h plus h squared over h, and that equals limit as h approaches 0 of, and what will happen next is we'll factor an h out of the numerator, which divides out the factor of h in the denominator, leaving us with negative 4 plus h, and now we evaluate the limit as h goes to 0, and when that goes to 0 we are left with negative 4. So the slope of the tangent line at x equals -2 is equal to -4. So we have the slope of the tangent line being -4. Our x value is -2. To find the y coordinate, f of -2 is +4. Again, our function is f of x equals x squared, so f of -2 would be +4. So we now have the point -2, 4. We have the slope -4. So now we want to find the equation of the line that has a slope of -4 and passes through the point -2, 4. A couple different ways of doing this. We can start with y equals -4x plus b. Plugging in our values, we know that 4 is equal to -4 times -2 plus b. That tells us that our b value is -4. So the equation of the tangent line would be y equals -4x minus 4. Now let's find the equation of the normal line. The slope of the tangent line is equal to -4. Normal lines are perpendicular. So slopes of perpendicular lines are opposite reciprocals of one another. So the slope of the perpendicular line would be +1/4. So now we want to find the equation of the line that has a slope of +1/4 and passes through the point -2, 4. So again, using y equals mx plus b, we know that y equals 1/4 x plus b, and we know that when x is -2, y is 4. So we get 4 is equal to +1/4 times -2 plus b. And solving this equation for b, we get a b value of 9/2. So putting this all together, we get the equation y equals 1/4 x plus 9/2. That would be the equation of the normal line. On the next slide, here we have the graph of f of x being the parabola. Here we are at the point -2, 4 right here, and as you can see, graphing both lines, graphing the lines, the tangent line, which was y equals -4x minus 4, we get the line that you're seeing here that's tangent. And then when we also graph y equals +1/4 x plus 9/2, here we get the graph of the normal line appearing as well. One application of this material is speed. Let's try an example. Free falling. A rock breaks loose from the top of a tall cliff and falls 16 t squared feet after t seconds. How fast is it falling 1 second after it starts to fall? So let's find our limiting value m, which would equal the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. That gives us limit as h approaches 0. F of 1 plus h would be 16 times the quantity 1 plus h squared minus f of 1, which is 16 times 1 squared all over h. That gives us limit as h goes to 0. What we'll do next is we'll expand the binomial 1 plus h squared, multiplying each term by 16. Gives us 16 plus 32h plus 16h squared minus 16 times 1 squared is 16, all of that over h. And now you can see in the numerator 16 and minus 16 gives us 0. So we have limit as h goes to 0 of 32h plus 16h squared all over h. We'll now factor out a factor of h out of the numerator, which will cancel or divide out the factor of h in the denominator. So that gives us the limit as h goes to 0 of 32 plus 16h, and now we let the limit as h goes to 0, causes this whole term to go to 0, leaving us with 32, and the units would be feet per second. So the velocity would be 32 feet per second. An object is dropped from the top of a 100-meter tower. Its height above the ground after t seconds is 100 minus 4.9 t squared meters. How fast is it falling 2 seconds after it is dropped? So our limiting value m is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. This is equal to limit as h approaches 0 of 100 minus 4.9 times the quantity 2 plus h squared minus the quantity 100 minus 4.9 times 2 squared all over h. This is equal to limit as h approaches 0. We're going to go ahead and expand the binomial, the 2 plus h, the quantity squared, and then multiplying each of those terms times the negative 4.9. So we would get 100 minus 19.6 minus 19.6h minus 4.9 h squared. Now we'll take care of this part of the numerator, so we'll distribute the negative through and also take the 4.9 times 4. That's going to give us a negative 100 and a positive 19.6 all over h. Now look at the numerator. We have a 100 minus 100, which makes 0, and we also have a negative 19.6 and a positive 19.6, which make 0. So now that gives us limit as h approaches 0 of negative 19.6h minus 4.9h squared all over h. Now we'll factor an h out of the numerator, which divides out the factor of h in the denominator, gives us limit as h approaches 0 of negative 19.6 minus 4.9h. And now we will let h go to 0, which causes this whole term to go to 0, leaving us with negative 19.6, and those units would be meters per second. So after 2 seconds, it is falling at 19.6 meters per second. In this lesson, we explored rate of change, tangent and normal lines and slopes. Be sure to work the exercises that your teacher assigns, and we'll see you next time.